Hello everyone. Today we are going to revise all the important formulas and the concept of the chapter work energy power part 1. So the work done is equal to F dot D cos theta, where F is the force, D is the displacement, not the distance, and cos theta is the angle between them. Next, when force is a function of distance, we can integrate it with respect to dx and we can find the value of the work done. Next, work done by centripetal force is equal to 0 as because the angle between the direction of the force and the direction of the displacement is 90 degree. So the work done would be equal to 0. Next, the dimensions of the work are the dimension of the force multiplied by the dimension of the displacement. So, the dimension of the force is ml t to the power minus 2 and the dimensions of the distance, as you know, is L. So, the dimension of the work would come out to be ml raised to the power 2 and t raised to the power minus 2. Next, as you all know, the formula of the kinetic energy is half mv square, which is also equal to p to the power 2 by 2m, where p is the momentum of the body. Next, the work can also be done by frictional force. So, what would be the value of that? That would be frictional force multiplied by the distance through which the body has travelled. So, as you know, the value of the frictional force is mu mg, where mu is the coefficient of kinetic friction and m is the mass and g is gravity and s is the distance. If the whole kinetic energy possessed by the body is vanished or opposed due to the frictional force, so we can say that the work done by the frictional force is equal to the initial kinetic energy of the body, and we can equate this in an equation. S into mu mg is equal to half mv square. So from here guys, we can find out the value of the stopping distance, which would be half mv square by mu mg. Guys, now the above all expressions were for the force which was constant in value. What if the force is not constant? For example, spring force is not constant and the value of the force changes as the spring compresses or the spring expands. So, the value of spring force is F is equal to Kx, where K is spring constant and x is displacement. So guys, what would be the value of the work done by the spring force? So for that we have to integrate force with respect to dx. Here W would be equal to integration of kx dx from 0 to x, which would be equal to half kx square. Now guys, here there could be two cases. If the work is done by the agent from the external side, so the work would be positive as shown in this diagram, and the graph would be above the x-axis. And if the work is done by the spring, then the work would be negative and the graph would be below the x-axis as shown in this diagram. Now next, coming to work energy theorem. What work energy theorem state is work done by all the forces on an object is equal to the change in its kinetic energy. So the change in kinetic energy is equal to work done. So what would be the change in kinetic energy guys? Half mv final square minus half mv initial square, where v final is the final velocity and v initial is the initial velocity. Now coming to the concept of potential energy, if we throw a body up the potential energy gets stored in a body by virtue of its height. So when a body is traveling upside, the gravitational force is doing the negative work on it, and when the body is traveling downwards, the gravitational force is doing positive work on it. So this change in potential energy gets stored in body, and which was a result of the work done on the body. Now if the body is dropped from some height, so its final kinetic energy would be equal to its initial potential energy. So from here we can find out the value of final velocity of the body by this equation. Next, law of conservation of mechanical energy, which states that K initial plus U initial is equal to K final plus U final. Guys, what it means is the sum total of initial energies equal to sum total of final energies in a body. For example, we have a block resting on the top of this wedge. When it comes down and hits this spring, the initial potential energy of mgh gets stored in the spring in form of half kx square. Thus, the energy is conserved. In next example, we can see that the block has been released from some height, and when it comes down, it travels a height of L minus L cos theta. So here this change in potential energy mgh, where height is equal to L minus L cos theta, gets converted into half mv square, where v is the velocity of the body at this point. Next, coming to the concept of power. Guys, the power is amount of energy transferred per unit time, and it is dot product of force and velocity, where if the theta is equal to 0 degree, we can write power to be equal to simply Fv. Guys, if we put force is equal to ma, where a is acceleration and m is the mass of the body, the expression of the power comes out to be P is equal to mav. Again, if we put acceleration is equal to dv upon dt, we can write it as P is equal to mdv upon dt into v. On rearranging, we can make this equation as P by m dt is equal to v dv, and we can integrate on both the sides, and while integrating we can find that this time gets converted into the whole time duration, total time, and this expression of v dv would become v square by 2. So guys, from here we can find out the expression of the velocity if we are given power, total time and the mass of the body from this equation. V is equal to under root of 2pt m 2pt divided by m. Guys, here are some value which will help you to convert kilowatt hour to joule and horsepower to watt or kilojoule. 1 kilowatt hour is equal to 3.6 into 10 raised to power 6 joule, and 1 horsepower is equal to 746 watt, or say 3 by 4 kilowatt. Guys, let me explain you another concept of average power, which is the total work done divided by total time taken. Also, the power is equal to dw by dt, where dw is equal to f dot dx, where dw is the momentarily work done or the little work done in the little span of the distance, which is dx. Guys, on putting the value of dw into this equation, we can find this expression p is equal to f dot dx upon dt, or we can write dr upon dt is equal to f dot v, where v is nothing but velocity. So from here we have also found out how we can say that the power is equal to f dot v. Next, if we have two different springs P and Q, and the spring constant of both are Kp and Kq respectively, so what would be the different work done in both the cases for the same amount of the distance? That would be F is equal to Kx. Work done in P would be more, guys, than Q, as the Kp is more than Kq. If we deduce the value of x in terms of f by k and we put it in the expression of work done, w is equal to half kx square, we get this expression half k f square by x square, which comes out to be half fx. Guys, from here we can see that the work is inversely proportional to the spring constant. Guys, there are several times question asked on this concept, so this is the important concept. The part 2 of the video would be bought soon. Thanks for watching this video. Have a nice day.